Welcome to all of you in this lecture. In this lecture we will discuss about group homomorphism. So suppose G1O1 is a group and G2O2 is another group. A map F from G1 to G2 is called group homomorphism if F of x O1 y is equal to Fx O2 Fy, where this x and y are the elements of the domain, and you know what is domain is G1, so x and y belongs to G1, and because x and y belongs to G1 and the operation of G1 is O1, so there is an operation O1 here, and Fx and Fy belongs to G2 and the operation in G2 is O2, so there is an operation O2 is here. So it simply means that the image of composition of two elements is equal to the composition of image of those elements, although the composition is different according to the group. So such a map is called group homomorphism. This map is also called a structure preserving map. This word homomorphism you will see in several places, like ring homomorphism. So ring homomorphisms are structure preserving maps of rings. Field homomorphism are the structure preserving maps of field. Similarly, vector space homomorphisms are the structure preserving maps of the vector spaces. Similarly, group homomorphisms are the structure preserving maps of the groups. So what is the structure in the group? The structure is algebraic structure, that is due to the operation in the group. So those maps which preserves those structure or operation is called group homomorphism. Okay, some of the things we need to remember. For example, what is endomorphism? So if F from G1 to G2 is a group homomorphism, then that group homomorphism is called endomorphism if G1 and G2 both the groups are same. This map is called monomorphism if this map is injective group homomorphism. This map is called epimorphism if this is surjective group homomorphism. This map is called isomorphism if it is bijective, that is 1 on 2, that is injective plus surjective group homomorphism. So isomorphism is bijective group homomorphism. And what about isomorphism? What about automorphism? This is F is a bijective group homomorphism and G1 and G2 both are same group. Then it is called automorphism. There are some more notations. Hom G1 G2 is the set of all homomorphisms from the group G1 to G2. Homomorphisms mean group homomorphism. Odd G is F from G to G such that F is automorphism, that is bijective group homomorphism. And in end G the map is from G to G such that F is automorphism. F is homomorphism. So actually end G is the set of all endomorphisms of the group G and odd G is the set of all automorphisms of the group G. I will refer you the book by Ramjilal and the book by Damit and Foote, and of course other books are there, but these are two good books, and you can see homomorphism part from these two books. Now come to some examples. Suppose G1O1 and G2O2 are the two groups and E denotes the identity element of G2. Define a map from G1 to G2 as Fg is equal to E. So every element is going to the identity element of G2. This map is a group homomorphism and it can be checked easily. Suppose I take G1 G2 in G1, then G1O1 G2, the image of this is E, and E can be written as E O2 E, and because everything is going to identity, so you can say that in place of first E we can write Fg1 and in place of second E we can write Fg2, so it satisfies the property of group homomorphism. So F is a group homomorphism. Because everything is going to identity, so this map is called trivial homomorphism or zero homomorphism. Identity is usually called zero also, so it is also called trivial homomorphism or zero homomorphism. So zero homomorphism is what? Is actually an element of hom G1 G2, that is the set of all homomorphism from G1 to G2. And because it is from G to G, if we define it as G to G, then it is also an element of int G. Now come to another example. This is identity homomorphism I from G to G, defined as Ig is equal to G for all G in G. This is called identity map. This is also a homomorphism. I of X O Y, if you will put, then it is X O Y, and X in place of X we can write Ix, and in place of Y we can write Iy. So it is a group homomorphism. Also, because it is an identity map, so it is 1 1 and on 2. So this is an element of not only int G, but it is also an element of odd G, because it is bijective. So one thing you should always keep in mind, odd G are a special type of endomorphism. So odd G in any group is actually contained inside int G. So set of endomorphism is a bigger set. And odd G is particularly those automorphisms, those homomorphisms which are bijective. So this is odd G, and int G is all the homomorphisms. So it is a bigger set and it is a smaller set. Now, example number 3. Suppose I take n in n, and I take a map from Z to Z as fx is equal to nx. So n is a natural number, so we can write x n times x plus x plus x, and this is true for all x in Z. So we can easily check that it is homomorphism. So f of x plus y for x y in Z is equal to n times x plus y. It can distribute fx nx plus ny, and it is fx plus fy. So f is an element of int Z. One can also check that f is 1 1, but f is not on 2. So I am leaving it as exercise, and since f is 1 1, so you can call it monomorphism. Now example number 4. Now consider the set of all non-singular matrices, n cross n non-singular matrices over R. This is a group with respect to matrix multiplication, denoted as GLNR. And now take another group, R star dot. Now we have a map in between these two groups, and that map is called determinant map. So take a matrix and take its determinant, you will get a non-zero real number. So it will be an element of R star dot. Determinant map also has a property that determinant of A into B, if you will take, then it will be determinant of A into determinant of B. Now here this dot is an element, is the multiplication of R star, and this dot is the matrix multiplication, so it is an operation of GLNR. So it means determinant is a map from GLNR to R star dot, and this is actually a group homomorphism. Now in lecture group theory 9b, we have defined the kernel of a homomorphism. So I am leaving it as an exercise for you to determine the kernel of this determinant map. So determinant map is as an example of a group homomorphism, and as kernel is defined in group theory lecture 9b, so it is now your exercise to determine the kernel of determinant map. Now come to another example, example number 5. Suppose n is a normal subgroup of a group G. Now define a map Fn from G to G by n, as Fn of G is equal to Gn for all G in G. Then let us check that it is a group homomorphism. So take G1, G2, two elements in G, then Fn of G1, G2. Here in between G1 and G2 there is an operation of capital G. So by definition it is G1, G2 of n, but because it is a quotient group G by n, so in quotient group we know how the operation is defined, so we can write it as G1n into G2n, and G1n is Fn G1 and Fn G2, so it means it is a group homomorphism. Also every element of this quotient group is a coset, so the coset will look like xn, so every element of G by n will be of the form xn, where x belongs to capital G. So but by the definition of this group homomorphism, Fn of x is equal to xn, so it means this is also a surjective group homomorphism, so we can say that F is a epimorphism. Now let us determine the kernel of this map. So the kernel of this map Fn, so by definition kernel of Fn is equal to those G in G such that Fn of G is equal to identity of G by n, and identity of G by n is capital N. So it means by definition of Fn, Gn is equal to n and those G in G such that G belongs to n. But this is G in G such that G belongs to n, it means G intersection n because n is contained in G, so it is n. So what does it mean? It means that for each n normal in G, there exists a group homomorphism Fn from G to G by n such that the kernel of this group homomorphism is equal to n. So it means each normal subgroup is actually a kernel of some group homomorphism. Is it okay? We have taken a normal subgroup, we have defined a group homomorphism Fn from G to G by n, and the kernel of this group homomorphism is n. So it means each normal subgroup, given a normal subgroup, we can construct a group homomorphism Fn from G to G by n such that the kernel, this normal subgroup is the kernel of this group homomorphism. So each normal subgroup is kernel of some of the group homomorphism. One more thing you can thought, each homomorphism F has an associated normal subgroup, and that normal subgroup is nothing but the kernel of that group homomorphism. Okay. Now let us see the relation between isomorphism and multiplication table. Suppose G1O1 is a group and G2O2 is another group. These are the two isomorphic groups, suppose. So means there is a map F from G1 to G2. Let us think of finite group so that we can easily understand it in terms of multiplication table. So take G1 to be the group A1, A2, An and G2 to be another group B1, B2, Bn. And suppose the map F is F of Ai is equal to Bi for all I. Further, suppose if I compose some element Ai and Aj, then we are getting element Ak in the group G1. Let us apply F on both the sides. So F of Ai O1 Aj is equal to F of Ak, and because of this definition of F, it will become Bk. Now by the definition of group homomorphism, we can write it as Fai O2 Faj is equal to Bk, but Fai is Bi O2 Bj is equal to Ak. It means in the group G1, if Ai O1 Aj is Ak, then in the group G2, Bi O2 Bj is Bk. So see both the expression. It seems that just if we replace A by B, then we will get the operation of the another group G2, and this is true. So everything is same between G1O1 and G2O2 except the symbol. So if we replace the symbol, so what this F is doing, F is just changing the symbols. And if G1 is isomorphic to G2, we denote it by G1, this symbol, isomorphism to G2. So whatever we told you now is that if I take Ai, let us see this is a multiplication table of G1O1. If we this is Ai and this is Aj, the product is Ak. If we replace every A by B, then Bi Bj is Bk. So once you know the multiplication table of G1, then you know the multiplication table of G2 if there is an isomorphism. In place of every symbol, suppose x in G1, replace it by fx in G2, you will get the multiplication table of G2. For example, suppose I have a group Z2 plus, then it has element 0, 1, its multiplication table is 0, 1, 0, 1, 0, 1, 1, 0. Now consider another group P2, that is the second root of unity. So there are two second root of unity 1 and minus 1 because their square is 1. This is again a group with respect to multiplication dot. So if we write the multiplication table of this group, then it will be 1 minus 1, 1 minus 1, 1 minus 1 minus 1, 1. Now if we define a map f from this group to this group such that f of 0 bar is 1 and f of 1 bar is equal to minus 1, then you can see this in place of this 0 bar you will write 1, in place of this 1 bar you will write this minus 1, 0 bar 1, 1 bar minus 1 and so on. If you will do it, then this whole multiplication table here, when you will put in place of 0 1 and in place of 1 minus 1, you will get this multiplication table. So it simply means that f is between these two groups is an isomorphism. So Z2 plus and P2 dot are isomorphic. Each and everything is same. The only difference is that the role which 0 is playing here, the same role 1 is playing here, and the role which my 1 bar is playing here, the same role is played by minus 1. Similarly, if you see the lecture 9D, in the lecture 9D we have calculated V4 by N, where V4 is the Klein's 4 group having 4 element EA, BC, and N is its subgroup EA. Of course it will be a normal subgroup, so there will be two coset N and Cn. For details you can see the lecture 9D of group theory. And when we will make its multiplication table, then its multiplication table will be NCn, NCn, NCn and CNN. So as you can see here, if you replace 1 by N and minus 1 by Cn, then this table will become this table. And similarly, if in this table, if you replace 0 by N, 0 bar by N and 1 bar by Cn, then this table will become this table. So it simply means that these two groups are isomorphic and similarly these two groups are isomorphic. So all the three groups are isomorphic to each other. So P2 is isomorphic to V4 by N, Z2 is isomorphic to V4 by N, and P2 and Z2 are also isomorphic to each other. So all the groups are isomorphic to each other. So it means in case of isomorphic group, symbols are different, but structure is same. Structure means operation, how they are composing. So for example, whatever 0 is doing here, the same thing is done by N here. And whatever this 1 is doing here, the same role is played by Cn. So isomorphic group has same structure, only difference is in symbol. If two groups are isomorphic, then all their properties will be same. All their properties means if one group has an element of order 2, then another group will also have an element of order 2. If one group has 4 elements of order 4, then another group will also have 4 elements of order 4. So all the property will be same. Commutator, if one group has a commutator G dash, then the commutator of another group will be the image of the symbols of G dash. So same order commutator will be in another group. So each and every property will be same, because the properties of the group are known by their structure. Structure means the multiplication table, and the multiplication table are same, just the symbols are different. So both the group has same structure, and every group theoretic property will be same in case of isomorphic groups. So it means if two groups are isomorphic, we need only study one of them because both have same structure. Now let us see another example. In lecture 90, we have calculated Q8 by H. Q8 is the quaternion group on 8 symbols having 8 elements: 1, -1, I, -I, J, -J and K, K, and H is its center, actually norm 1 minus 1. It is a normal subgroup, so we can make a quotient, and we have 4 cosets H, IH, JH and KH. If we fill its multiplication table, which has been left as an exercise in this lecture 9D, now if you have done it, then you can check whether you have filled it correctly or not. So if we make its multiplication table, then its multiplication table will look like this. And now we have a multiplication table of the group V4, that is Klein's 4 group. Now in both the groups, if we define a map from V4 to Q8 by H as E is going to H, A is going to IH, B is going to JH and C is going to KH, then you can see that this multiplication table will change to the multiplication table this. So it means this map is actually an isomorphism. So we can say that V4 is isomorphic to Q8 by H. So simply we can say that Q8 by H, that is this quotient group, is nothing but V4. So all the properties of this quotient group will be V4. I hope you don't have any problem in understanding these things. If you feel or face problem, then you can ask me in comment box. So thank you very much. We will meet in next lecture very soon.